Hello everyone, myself Miss Pranoti Khawane, Assistant Professor in Physics, Arts and Science College, Patur. Our today's topic is elasticity. So without spending much time, we will start our lecture and we'll see few concepts related elasticity. Okay, so what you will guys will get after completion of this PPT is to demonstrate your understanding of elasticity, plasticity, elastic body, plastic body, stress and types of stress, strength and its types, elastic limit, Hooke's law, Young's modulus, bulk modulus, modulus of rigidity and applications of elasticity. Again, you will be able to write and apply the formula for calculating Young's modulus, bulk modulus, modulus of rigidity. And last but not least, you will enjoy solving problems involving each of the parameters in the above objectives. Okay, so we'll start. First, what is the elasticities? We all have studied about rigid solid bodies, right? So what is rigid solid body? Where the distance between any two particles is always fixed. But real solid bodies do not exactly fulfill this condition. So when the external forces are applied, the body gets deformed. And when the body gets deformed, the internal forces are set up and they try to restore the body in its original shape. Okay. So the extent to which the shape of body is restored when the deforming forces are removed, this varies from material to material. The property to restore the natural shape or to oppose the deformation is nothing but elasticity. So we will club the elasticity in our words as the property of material by virtue of which body or material opposes the change in its shape and size and regain its original dimension as soon as the deforming forces are removed is called elasticity. Okay, so here are the two examples. First example is of spring and second is of rubber. So you apply stretching forces or compressive forces, and whenever you remove these forces, these deforming forces are removed, you will find the spring at its static position. Or the same thing happens with rubber even. Okay. So we should think microscopically now. So what is the microscopic reason of elasticities? We all know any body is made up of large number of molecules or atoms which are arranged in regular fashion. Okay, so whenever the deforming forces are acted upon them, these molecules or atoms, they get displaced from their original position, right? Each molecule is bonded to its neighboring molecule with some force of attraction. Okay, whenever the deforming force act on them, they get displaced from their position and the distance between them gets changed. So the restoring forces start acting on the molecules and they bring them back to their original position, and the body in this way gets its original shape. So this is the microscopic reason behind elasticity. Let's move. What is plasticity? You can call it as anti-property of elasticity also. So let's study about its definition. Is property of material by virtue of which a body or material cannot regain its original shape and size after removal of deforming forces. Okay, so here are few concepts of elastic body and plastic body. Yes, exactly. Its name itself suggests what is elastic body and what is plastic body. So the body which completely regains its original dimensions when deforming forces are removed is called a perfectly elastic body, and the body which does not regain its original dimension when the deforming forces are removed is called plastic body. Okay, so let's move towards the concept is stress. So what is stress? We all face various kinds of stress in day-to-day life. So how the material in the universe could be without stress, isn't it? Okay, so let's study the stress in materials. Okay, so what is stress in very easy language? We can define it as ratio of internal restoring force per unit area. Okay, the internal restoring force in an elastic body per unit area is called stress. So we know the body remains in equilibrium in deformed state also. So therefore the internal restoring force are equal to the applied forces then, and thus we can modify the formula also as stress is equal to the ratio of applied force per unit area. So the CGS unit of stress is Dyne per centimeter square and SI unit is Newton per meter square. So here are the types of stress. First is tensile or longitudinal stress. Second is volume stress, and third one comes as shearing stress. So what is tensile stress? If deformation causes the change in length of the body, then the stress is called tensile stress. Okay, so mathematically we can express as tensile stress as force per unit area. Okay, then comes the volume stress. So when deformation consists of change in volume of the body, then the stress in it is called as volume stress. So mathematically we can express as volume stress is equals change in pressure. And last one, shearing stress. When the deformation consists of change in shape of the body, then the stress is called as shearing stress. Okay, so mathematically it is again force per unit area. Okay, then next comes strength. So what is strength? We can define strength as change in dimension per unit original dimension. Okay, so change in dimension per unit original dimension is nothing but the strength. Let's move towards types of strength. So associated with each types of strength that we explained earlier, there is a corresponding type of strain also. Okay, so first comes tensile or longitudinal strength, then comes volume strength, and after then shearing strength. So what is the longitudinal strength? So here is the mathematically we can state that tensile strength is the ratio of change in length per unit original length. Okay, then I have shown an example here. Suppose some wire is there and I have attached some load there. Some wire is suspended and at its free end I attach some load, then its length get changed. So what will be tensile strain is its original length suppose is capital L and delta L is its change in length. So it will be delta L upon capital L. Okay, then volume strain. What is volume strain? The ratio of change in volume to the original volume is volume strain. So suppose original volume of the body be V and its volume changes by small fraction dV, then the volume strain we can define as dV by V. Okay, then shearing strain. the ratio of lateral displacement of any layer of the body, lateral displacement of any layer of the body to its distance from fixed layer. This is nothing but the shearing strength. Okay. So here's we have to define some stress strain curve, and you will be able to know few concepts here. Okay. So what is this stress strain curve is? You guys can see here some blue region is there where Hooke's law is shown, and that is called as elastic region, and another is plastic region. Okay. So here comes first the proportional limit, then elastic limit, then yield point, then ultimate stress point, and then fracture or breaking point. So the first is our proportional limit. So what is proportional limit? Here the object obeys the Hooke's law. So new concept we have introduced with here, that is Hooke's law. So within the elastic limit. Okay. So again we have to find out what is the elastic limit. So it is the maximum stress to which a body can be subjected without permanent deformation. It is called elastic limit. Okay. So in that elastic limit, stress is directly proportional to strain. Okay. Stress is directly proportional to strain, or ratio of stress to strain is constant, and this constant is called modulus of elasticity or coefficient of elasticity or elastic constant. Okay. So modulus of elasticity is defined as stress to strain or ratio of stress to strain. Okay. So we have learned the Hooke's law, and we have find out what is the proportional limit. Okay. Then what is elastic limit? So here in figure you can see point A shows you the proportional limit, then point B shows you elastic limit. So what is the elastic limit? Point up to which body regains its original shape is elastic limit. Okay. Then point C. What the point C shows? Lower yield point. Okay. Or yield point. So what is yield point? The point from which material starts deformation is yield point. Next, the ultimate stress point. What is ultimate stress point? The point representing maximum stress before breaking is ultimate stress point. And last is E, that is fracture or breaking point. The point where the material breaks is fracture point or breaking point. Okay. Next we will move. What is Hooke's law? We have seen. Okay. So Hooke's law, what it means? Within the elastic limit, stress is directly proportional to strain. We have seen. Okay. And ratio of stress to strain is, this gives us modulus of elasticity or coefficient of elasticity or elastic constant. What is its CGS unit is Dyne per centimeter square, and its unit is Newton per meter square. Then types of modulus of elasticity is Young's modulus, bulk modulus, and modulus of rigidity. So we'll see what is Young's modulus. Okay. So what is Young's modulus? So suppose here I have shown some wire. Okay. So the basic definition of Young's modulus is it gives the relation of tensile stress to tensile strength. So it is the ratio of tensile stress to tensile strength, and ratio of tensile stress to tensile strength is nothing but the Young's modulus. Okay. So suppose I have a wire with length capital L and having radius R, and is suspended from some rigid support, and at its free end if I attach some weight or mass having its mass as m, then we will find there is a small increase in its length, means length of wire. Okay, so finally we will get equation as y is mg capital L upon pi r square small l. Young's modulus, this is the property possessed by this modulus is possessed by solids only. Okay, then we will move to bulk modulus. So what is bulk modulus? This gives the ratio of volume stress and volume strain. That is, ratio of volume stress to volume strain is nothing but the bulk modulus. Suppose that a body of volume capital V is subjected to additional small pressure, we will see del P. Then the increase in pressure will produce decrease in volume. Okay, let dV be decrease in its volume. So volume stress is, we know what is volume stress, change in pressure, and that will be shown as dP, and volume strain is change in volume per unit original volume, that is dV by V. So mathematically we will get the final equation for bulk modulus is minus V dP by dV. So it is possessed by solids, liquids and gases, all the three. Okay, then it comes modulus of rigidity. So it gives the relationship between shearing stress and shearing strain. So what is modulus of rigidity? Ratio of shearing stress to shearing strain, and we denote it as with eta, that is F upon or F by A theta, and is also possessed by solids only. Okay.
Applications of elastic behavior of materials. In this module, you will learn about different applications of elastic behavior of materials. You might have seen a crane lifting heavy loads on a construction site. The cranes have a thick metal rope so that the attached load does not break the rope under the stress. This happens because the stress produced by the load is less than the elastic limit of the rope. Thus, the cranes are designed to reduce the stress by varying the diameter of the rope as per the elastic limit of the material of the rope. Just like cranes, bridges are also designed in a way that they are not affected by the stress of the load. However, after many years of use, cracks occur in the bridges. This happens because the bridges lose their elastic strength due to the continuous stress produced by the load. Such bridges become unsafe for use. The special design of the bridges we are referring to make use of beams. The beams used in bridges play an important role in reducing the stress such that they can withstand the huge load of moving traffic and people. Let us understand how. Let us consider the case of a beam loaded at the center and supported near its ends as shown. The beam of length L, breadth B and depth D when loaded at the center by a load W sags or bends by an amount delta given by the following formula, where Y is the Young's modulus of the material. We can see that to reduce the bending or to increase the elastic limit of the beam for a given load, we should use a material with a large Young's modulus Y. For a given material, as you can see from the formula, increasing the depth D can reduce the bending to a great extent. But on increasing the depth, the bar may bend as shown. This is called buckling. To avoid buckling, change in both the breadth and depth are made and an I-shaped beam flange is used. This section provides a large load-bearing surface and enough depth to prevent bending. This shape reduces the weight of the beam without affecting its strength. Due to the same reason, a bridge is designed with eye-shaped girders so that it does not bend or break due to the load of the moving traffic. The railway track beam's cross-section is also of eye shape so that it can withstand the load of the train. Not only the beams, but the pillars or columns in buildings and bridges are also designed to reduce stress. A pillar with rounded ends supports less load than that with a distributed shape at the ends. So, distributed shape pillars are preferred over rounded end pillars. Let's recap. There are many applications of elastic behavior of materials. Some of them are use of thick metal rope in cranes, use of eye-shaped beams in bridges and railway tracks, preferred use of distributed end pillars over the rounded ones.
We concluded of our today's topic. So I hope you all got few things or few concepts clear from today's lecture. So I would like to offer my sincere thanks to Principal Dr. N.S. Thakre sir, MSP Arts Science and KPT Commerce College, Manora, District Washing, as well as I am thankful to Head of the Department of Physics, Dr. K. Koparkar sir, as well as my co-colleague, Mr. Nikhil Bhagat, as you guys have given me the chance for a guest lecture here. Thank you so much everyone for your peaceful cooperation. Thank you once again.